Welcome to the second part of the Z procedure activity, Lab 6. In Part A, we looked at the three assumptions of the Z procedures. That's the data are independent, they come from a normally distributed population, and we know the population variance. Under those circumstances, the Z-test, the p-values for the Z-test, were uniformly distributed, which is exactly what they need to be if the test is always appropriate. We also discovered that the observed rejection rate was really close to alpha. And that's what we would need if all we really care about is the rejection rate when alpha is 0.05. In part B of this lab, in this part, we're going to violate one of those three assumptions. We're going to violate the normality assumption. We're going to make sure that the data come from a non-normal distribution, for instance, the uniform distribution or the exponential distribution. And we're going to look at the distribution of those p-values from the z-test when the data are not normally distributed. If the distribution of p-values is uniform 0, 1, then that assumption is not important. We're also going to look at the rejection rate. If the observed rejection rate is close to alpha, then we're going to conclude that, hey, under these circumstances, that assumption of normality is not important. And what we're actually going to discover is that we can violate the normality assumption, and things will work, usually, as long as our sample size is large enough. And that gave rise to what a lot of the books are saying. As long as n is equal to 30 or 50 or pick your number, you can use the z-test. We're going to find out about that in this part of the activity. So let's continue the structure. Make sure that we do have a script B, or that we do start up R, set the working directory, create a script B, save it. Might as well put this lab, this is part 2 or part B of the lab. Again, recall that the z-test has those three assumptions: that the measurements are independent, that they are normally distributed, and that we know the population standard deviation or the population variance. And under those circumstances, we can test three different null hypotheses. We can test if mu is equal to a given number. Mu, again, is the population mean that we're trying to draw inference about. And mu naught is a hypothesized number. So this could be mu equals 2, mu equals 5, mu equals negative 19. So that's one. That's actually called a non-directional hypothesis or a two-tailed hypothesis. We can also test null hypotheses of the form mu is less than or equal to mu naught. And we can calculate hypotheses of the form mu is greater than or equal to mu naught. And again, mu naught is a specified or hypothesized value. Mu is the population parameter that we're asking about, the mean. As stated in the previous part, in part A, since we are talking about testing, the key statistic to measure from the z-test is that rejection rate. Rejection rate is just the proportion of the time that our p-value is less than our specified alpha. And again, alpha will be 0.05 for us. Now that rejection rate, that observed rejection rate, should be exactly alpha. But because of the randomness that's in life, it's going to be close, or it should be close to alpha. At worst, it should be less than alpha. If it's greater than alpha, then what we're saying is that we are rejecting more often than we state. So we claim that we're rejecting incorrectly 5% of the time, but in reality, we may be rejecting more often than that. And that's actually a statistical sin. That's one of the bad ones. We could also test if the p-values are uniformly distributed, for the same reason that in the previous lab. So in this part, we're going to violate that second assumption, the assumption of normality. We're going to draw our data, still independent, and still with a known standard deviation, but we're going to draw our data, in this case, from an exponential distribution. And without loss of generality, we'll draw it from an exponential with lambda equal to 1/2. Lambda is also called the rate parameter. It's equal to 1 over the mean, which means that the mean of x is going to be 2. And one of the neat aspects of the exponential distribution is that the mean and the standard deviation are the same. So the mean is 2, and so is the standard deviation of the population. Now note that this is a violation of one of the assumptions of the z-test. But how bad of a violation is it? If all we have on our desert island is the ability to do a z-test, and we know that our data is exponentially distributed, are we committing a sin? Can we still get away with doing a z-test if our data is exponentially distributed and our sample size is 50? Well, let's see. Recall from the previous part that the Monte Carlo part, or the simulation part, consisted of these 5 lines. Line 3, we're drawing our random data. In the last part of the lab, we were drawing a random sample from a normal distribution with a sample size of 50. The mean was 2 and the standard deviation was 5. In this part of the lab, we're going to change this up a bit. We have to draw it from an exponential of lambda, or the rate, equal to 1/2. The 4th line, we are calculating the p-value. We're performing the z-test under the null hypothesis, calculating the p-value, and saving it. Now, I do have to specify that we're doing the z-test under the null hypothesis. We're violating one of the assumptions, but the z-test is still tested under the null hypothesis. Specifically, that we know that we have the correct mean. And then the loop means that we're going to be doing this 10,000 times. At the end, we're going to have a vector of 10,000 p-values. And then we can test the rejection rate, hope that it's close to alpha. We can use the Kolmogorov-Smirnov test to see if the p-values are uniformly distributed. So there's 2 changes. One happens where we're drawing our sample, and the other happens in our z-test statement. So let's put this over into R. And this is what we had last time. We're going to change it to an exponential distribution. Still a sample size of 50. For an exponential, the rate we're specifying is 1/2. Since the rate is 1/2, under the null hypothesis, that means that the mean is actually 2. It also means that the standard deviation is 2. Now, if we run this, and we just started R, by the way, if we run this, we're going to get an error. Now, watch this. I'll highlight, Control R, whoops, could not find function z-test. Remember, we have to import that function specially. We got to source it from that website, from that directory, and that's the name of the test. So now that we've run that, and I Control R'd this, you can see over on the left. Can hit Control R again, and it's running. And for my computer, that took about 1.5 seconds. It may take longer on yours. It probably will take longer on yours. But now what we can do is we can look at all the p-values. Notice my cursor is over here on the console window. So I type p, hit enter. Those are all the p-values. Those are all the values that are stored in the p vector. Seeing them all doesn't really help us too much. Let's look at a histogram of p. Oh, there's a histogram of p. It looks like it could be flat. I'm not too sure. There's a lot of jaggedness. And that jaggedness comes from the fact that we're only using 10,000 iterations of this. If we upped it to 1 million, that would be much smoother. And it would be much easier to interpret. Let's get rid of that. Let's do the rejection rate. Recall that we're going to reject if the p-value is less than 0.05. And to calculate the rejection rate, it's just the average of those, so the mean. So our observed rejection rate is 0.0476, which, using the power of 100 rule, comes out in this case to be 0.05, because 10,000 is 100 to the power of 2. So we get to keep 2 digits after the decimal place. And 0.05 is alpha, so I'm doing a little dance here, kind of like I do in class. We could also use the Kolmogorov-Smirnov test to see if this test under these circumstances is appropriate for any alpha value. So it's KS test of P unif, and P unif is in quotation marks. Control R. Notice that the p-value for the Kolmogorov-Smirnov test in this case is 0.284. which is greater than alpha, which tells us that there is no significant evidence that this is a bad test under these circumstances, which could be kind of surprising. I mean, we're making the assumption for this test, we're making the assumption of normality that the data come from a normal distribution, but in this case, we drew our data from an exponential distribution. So we violated that assumption, but the test still works. And the reason actually is because of the sample size. 50 is, quote, large enough in this case. Remember, the central limit theorem helps. Now if we move on to 3, we're going to change that sample size from 50 to 30 and rerun it. Now I don't need to rerun the source because R already knows that the z-test is a good function. Control R this, wait for a second and a half, there we go, and look at the p-values. Again, 10,000 iterations, not going to be too easy to determine a pattern. Could be that this first bar is a little too low. I don't know. It could be due to the variation. We can calculate the observed rejection rate. It's 0.046. This is, again, 10,000, which is 100 to the power of 2. So we round to 2 places, 0.05. That's nice. And the Kolmogorov-Smirnov test gives us a p-value 0.5228, which is large enough. It's greater than alpha. Therefore, again, no evidence that this test is inappropriate. So even on a sample size of 30, we can get by with using the z-test. Finally, let's do it with just a sample size of 5. Control R to run it. Takes about a second. Let's look at the histogram. Okay, now I'm starting to see a pattern here. It looks like it's dropping down quite a bit early. Let's see what that rejection rate is. 0.0438. Round that to 2. That's 0.04. So it's not horrible. We're rejecting too rarely. But it's still not 0.05. And the Kolmogorov-Smirnov test says, no, it's not uniformly distributed. I mean, the p-value is 1 times 10 to the negative 9th, which if we were to write that out, that would be 0.00000001475, which is definitely less than alpha. So if the sample size is 5, this is not an appropriate test. But it seems like if the sample size is 30, it is an acceptable test. So what's the difference between steps 2, 3, and 4? Only the sample size. I mean, we kept the exponential distribution, didn't change that. We kept the rate, didn't change that. All that changed was the sample size. So a sample size of 5, not enough sample to allow the central limit theorem to, quote, kick in and fix the non-normality. Sample size of 50, definitely. Sample size of 30, well, when we did it here, it worked. When I did it when I was writing at the lab, it didn't work. When you're doing it, it may work, it may not work. So 30 is right there on the bubble. So it's better to do more than less, but hey, sometimes all you've got is 30 data points. So in this second part of the 6th laboratory activity, we show that the z-test can still be appropriate even when the data do not come from a normal distribution. That is, we can still use this test even if not all of the assumptions are met. Specifically, the assumption of normality can be violated, and as long as the sample size is large enough, it seems to work. Well, technically, as long as the sample size is large enough and the data are exponentially distributed. What if the data comes from a different distribution? Is the z-test still appropriate? Well, I don't know. Depends on the distribution. I can give you a distribution where the z-test definitely won't work no matter what the sample size is. But I can also give you a distribution where the z-test will work no matter what the sample size is. So it depends upon the distribution of the data and the sample size. When we used the exponential, a sample size of 5 was too small. Sample size of 50 was good enough. In the next part of the laboratory activity, we're going to violate a second assumption, which is actually third on the list. And that's the assumption of knowing the population standard deviation. Whereas the distribution of the measurements was not too important, thanks to the central limit theorem, the knowledge of sigma is very important. And we're going to find that a sample size is of 50 not going to cut it under most circumstances. So I hope this was helpful. Remember to save the script as script B, and I will see you later.